All right, hello everybody. Sorry I can't be here today, but here we go. Let's talk about the derivative and the tangent line problem. So what's the problem? We actually looked at this problem very briefly at the beginning of Unit 1. We didn't do too much with it. Now we're going to do something with it. So let's remind ourselves what the tangent line problem is. And that is basically, if we have a straight line, we know how to find the slope of the line. You just do rise over run, and you can find the slope of the line. You just pick any 2 points, find the rise, find the run, and then slope is rise over run. But what do you do when you don't have a straight line? Which probably safe to say happens more often than not. You have a curve instead. So we can't really talk about the slope of the curve, but instead what we can do is we can find a point on the curve and then find the slope of the tangent line. And then that's going to change, of course, depending on where you are on the curve. So if I'm right here, then we can see that this would be the tangent line, or it appears to be close. I don't know if that's exactly it. But, if I'm over here, then the tangent line is somewhere like this, has a totally different slope to it. So the slope is going to change as you go through the curve. And so that's what we're going to learn today, is how do you find the slope of this tangent line? Not just an approximation, which is what we did last unit at the beginning. Now we're going to be able to find the exact thing. So how are we going to do this? With limits, of course. Sorry, limits aren't gone yet. We will eventually phase away from limits, but we're still in the world of limits. Okay, so let's draw a different picture here and kind of get a better idea. So let's investigate the problem further. So let's say that we have a curve, something like an exponential function. Something like that. And let's say that we want to find the slope of the tangent line right here at whatever this x value is. Now, we don't know exactly what the tangent line is. Our slope formula requires 2 points. When we do y2 minus y1, we need the y coordinates from 2 different points. And if we're just looking at the tangent line, we only have 1 point. So how do we find the slope of a line when you only know 1 point? Well, what we can do is we can approximate this. We can start with an approximation. Now I'm going to go ahead and call this point P on the curve. And I'm going to take another point somewhere else on the curve. I'll call that point Q. And point Q, let's try to make that a little more straight. When I look at its x-coordinate, I'm going to call this x-coordinate x plus delta x. The distance between x and x plus delta x is delta x. If you're not used to seeing delta x, by the way, you'll see it a lot in science and math formulas. The delta, that's actually a Greek letter delta, the triangle, and that means change. Anytime you see delta, think change. You may have actually seen that in the slope formula. So slope formula can be thought of as the change in the y values over the change in the x values. But instead of writing out the words change in y, we can just say delta y over delta x. So change in y over change in x. But like I said, you'll see the delta a lot in science and math formulas. So if I add delta units to x, then this would be x plus delta x. So I've got these 2 points, and now that I have 2 points, I can actually find the slope of the secant line instead. And so let's see if I can get these a line through points P and Q. Not bad. All right, there we go. So this is our secant line, and this is our tangent line. And the idea is if we can make delta x smaller and smaller and smaller, that's going to move this point closer and closer and closer to x, which will move point Q closer and closer and closer to point P, which will then bring the secant line down to the tangent line, and then we can use that idea to find the tangent. Now I know it's hard to see what I was talking about there, so I'm going to go to Desmos for a second. So I basically have the same picture here. You can see x down at the bottom. Sorry, I can't point now with my pointer, so you kind of have to go with it. So I'll just kind of describe what you're looking at right now. But you can see at the bottom of the screen, actually, let me turn off the numbers. But you can see the bottom of the screen, below point P, we have x, and then below point Q, you can see x plus 1.21. So right now they're 1.21 units apart from each other, and I can move point Q along here. If I move it further away, you can see now we have x plus 1.94 at the bottom. So that plus whatever is going to get bigger the further away x gets. But if I can bring point Q closer to point P, then that point gets closer to x at the bottom, and that value becomes smaller. Now take a look at what's going on with these two dotted lines. See, the red line is the secant line, and the green line is the tangent line. As point Q gets closer and closer to point P, see how that secant line begins to approach the tangent line. And if I could get them right on top of each other, they would be the same line. So the closer Q gets to P, the closer the secant line gets to the tangent line. Or we can say it using some of the vocabulary we started using last unit. As Q approaches P, the secant line approaches the tangent line. As Q approaches P, the secant line approaches the tangent line. I'm going to go ahead and go back to our notes now. Let's write this down. So as Q approaches P, the secant line approaches the tangent line. Another way of saying Q is approaching P is, if I can make this distance smaller, that makes Q approach P. And again, if I go back to Desmos, that 1.8 down there, that represents my delta x. As Q approaches P, the change in x is approaching 0. So instead of saying as Q approaches P, I can say as delta x approaches 0, the secant line approaches the tangent line. And then we can actually say the slope of the secant line approaches the slope of the tangent line. And so let's actually put that now in terms of our limits that we did last unit. So the slope of the tangent line is equal to the limit as delta x approaches 0 of the slope of the secant line. So we're starting to get closer and closer to a formula here. The slope of the tangent line is equal to the slope of the secant line as delta x approaches 0. So now all we need is a formula for the slope of the secant line. And we have 2 points. If we have 2 points, we can just plug them into our formula. So let's now also come up with coordinates for these points. So this, if we call this graph the graph of y equals f of x, then we can say the coordinates for point P, actually here, let me move this over. The coordinates for point P would be x, f of x, and then the coordinates for point Q would be x plus delta x, f of x plus delta x. The x coordinate is x plus delta x. Plug that into the function to get the y coordinate. And now we have our y2 minus y1 over x2 minus x1. So now we can go ahead and put this in a formula here. So instead of writing out the slope of the secant line, let's actually do our formula. y2 minus y1 over x2 minus x1. And then, oh, someone's in my driveway. Let me go ahead and put this on Do Not Disturb. All right, back to the notes. F of x plus, I'm just going to go ahead now and simplify that denominator. Because in the denominator, the x minus x will cancel out, and we're only left with delta x. And this probably rings a bell right here. This right here is our formula for the slope of the tangent line. So the slope of the tangent line is that. And really, that's the main point of the lesson. Now we're going to see how we use this. So if you need to, pause the video and kind of chew on this a little bit. But when you're ready, you can go ahead and push play. And we're going to go ahead and talk about what a derivative is. We've actually been talking about derivatives. This whole time that we've been listening to the video, we've been talking about derivatives. The derivative is equal to the slope of the tangent line to a curve. So every time I was talking about slope of a tangent, I was talking about the derivative. Slope of the tangent line, that's the derivative. So the derivative is equal to this limit. You guys were doing some derivatives in some of your problems last unit, and you didn't even know it. But now we know it. So the derivative of a function is equal to, the derivative of f of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And there it is. Now I know this idea of the slope of the tangent line and what the derivative actually means may still be a little crazy right now. Hopefully it'll make a little more sense by the end of the video, but we have this to work with right now. This is also called the difference quotient, this thing right here, not the thing with the limit. So just this part, and it's called the difference quotient, I think probably for obvious reasons. You have a difference right there, you have a quotient right there, so difference quotient. Okay. Let's talk about some notation for the derivative, and then we're going to do some examples. So if the notation for the derivative, we're used to seeing f of x. Well, if we put a little apostrophe right there, that means the derivative of f of x. You can also read this as f prime of x. So if you see this, it means the derivative of f of x. So you could say the derivative of f of x, but you can also say f prime of x, and then people know it's the derivative. If it's not written in function notation, if it just says y equals, you can say dy dx. And you can actually say that dy dx. Notice I'm not saying dy over dx, although technically it is dy over dx. Still, people just say dy dx. You'll also hear it, though, this one people will often say the derivative of y with respect to x. Y is the function, x is the variable in the function. That's what that means. So dy dx, derivative of y with respect to x. We can also say dy dx of f of x. You'll see this kind of notation. Whoops. And then also similarly, because we know that we could, instead of writing an f, you can have a y. So you have that, but then this is basically this notation. So you actually never see people write that when you're just talking about y, but people could put the function in there. And then the other thing, you'll get used to this notation, don't worry. Everybody gets used to it. It seems like a lot at first, but it's not. If we know what the function is, like maybe the function is the function x squared plus 2, you might also see the notation like this. So find the derivative of x squared plus 2. And again, they're saying with respect to x, so we know x is the variable in there. So these are some common notations for the derivative. Just get used to them because you're going to see them all over the place. But yeah, let's jump into an example now. So let's first find this. Now, all we're going to do is that that limit definition that I gave you. If you think you have an idea of how to do it right now, feel free to go ahead and just jump right into it. We're going to go ahead and work it out together, but yeah, feel free if you want to just pause the video for a second and try it on your own. So in case you're like not quite sure where to start, the derivative, remember that definition I gave you, the limit of as delta x approaches 0 of f of x plus delta x minus f of x over delta x. You'll get really familiar with this formula. So this is the one I'm talking about. F prime of x is just calculating that. So I really encourage you guys, because we did do problems like this last unit. You could probably do this on your own. All right, let's go ahead and take a look at it. Yeah, I've got it worked out down here. So here it is right here. So remember, if f of x is 6x plus 7, so f of x is 6x plus 7, then f of x plus delta x means you're going to take x plus delta x and put it in place of x. And that's what this is right here. And then from there, it becomes a little more straightforward. You can distribute the 6, and then I also distribute this negative sign. 6x minus 6x cancels, 7 minus 7 cancels. So we just have 6 delta x over delta x left. Now the delta x's cancel. And finally, We're just taking the limit of a constant, so the answer is that constant. And there it is. And by the way, if you think about this, it actually makes perfect sense now that we know what a derivative is. Remember, a derivative is the slope of the tangent line. This is a straight line. It has a constant slope everywhere. The tangent line won't change values, or the slope of the tangent line, so it's just 6. So there's our first example. Okay, here's a second example for you to try. Again, pause a video. If you didn't pause the video last time, definitely pause the video this time. Try it on your own before you see the answer. Okay, I hope you paused the video. Here's this one. It gets a little trickier because we have a complex fraction, same exact formula. Here's the formula right here. And again, f of x is just 1 over x. F of x plus delta x would be 1 over x plus delta x. And I haven't been saying this, but when you first have the formula, when you try to plug in delta x with a 0, you will always get 0 over 0. It's always going to be indeterminate, so you have to do something with it. So now we'll go ahead and multiply by the LCD so that we can cancel out. So when this thing multiplies here, the x plus delta x's cancel, and we just have 1 times x left. And then when you multiply this thing by 1 over x, the x's cancel out, and you just have minus 1 times x plus delta x. And then in the bottom, you just have delta x times x plus delta x. Simplify the numerator, cancel out the delta x's, and once you canceled out, try plugging in again, and you will find that you get negative 1 over x squared. Now notice, this time, we got another function, negative 1 over x squared. We had y equals 1 over x. Now we have this. So this is giving us the slope of the curve at any point. We'll take a look. There's an example we have at the end that I already have plugged into Desmos. We can take a look. Why are we getting x's? A lot of you guys were asking that last unit. And all I could tell you last unit was just that, well, these x's aren't approaching anything. Only delta x is approaching 0. So only this becomes 0. And when you simplify it, you get negative 1 over x squared. But now we'll actually get to see what that means. So some of you that didn't get a very satisfying answer from me last time, hopefully I'll give you a better answer this time. So there's example 2. All right, now there is an alternate form of the derivative. Sometimes you actually just care about the value of the derivative at one point and one point only. And if you already know what that point is, there's another form which is easier to work with. We can get that form by the same kind of picture we were dealing with before. So I'm just going to quickly draw this curve to help us investigate it. This time, rather than just putting a random x, I'm going to say that we're finding the slope of the tangent line at a constant, a. And then this point right here will move. So we have P, we have Q. I'm not going to bother putting any kind of delta x or anything in here. But as Q approaches point P, oh, I forgot to draw the tangent line in here. I mean the secant line. So here's the secant line, same kind of thing we had before. As Q approaches P, this secant line will approach the tangent line just like we had. So instead of saying as Q approaches P, we can say X approaches A. Because as Q approaches P, point X will approach A. So we can take the limit as x approaches a. And then we can do the slope of the secant line, just like we had before. So point Q has the coordinates x, f of x. Point P has the coordinates a, f of a. So y2 minus y1 over x2 minus x1 looks like, whoops, this, f of x minus f of a over x minus a. Oh, that's a wrong color. Oh, make me unhappy. It's got to match. y2 minus y1 over x2 minus x1. And this is the value of the derivative at a specific point. So this is the derivative of f of x at x equals a. When you evaluate this limit, it should be specifically the slope of the tangent line at x equals a, which means it should be a numerical value. You should never get x's for this. It's going to be a fixed constant, whatever the value of this slope is. So let's take a look at this. So what if I said, find the equation of the tangent line to f of x equals 2x squared minus 3 at x equals 1. So let's see if we can just kind of do a rough sketch to get an idea of what's going on here. So I know that the function is a parabola, and it's a parabola that if we take y equals x squared, it's been stretched vertically by a factor of 2 and shifted down 3 units. So the vertex is down at 0, -3. And then it's got, sorry, I just drew a blank here. 1, 2, 3, 4, 5. It's a very skinny parabola. So it looks something like this. And then at x equals -1, we're right here on the curve. Our tangent line looks something like that. It's pretty steep in the negative direction. So we expect kind of a large value. Let's see what it looks like. So the way you work with this is, so we're finding the derivative evaluated at -1, so the notation looks like that. And using that formula, it's the limit as x approaches a, which in this case is -1, of, actually, let me write the formula down. So I'm going to make those a's. This is the formula I gave you. F of x minus f of a over x minus a. And so if we plug in, we're finding the derivative evaluated at x equals -1. X is approaching -1. And it's f of x minus f of -1 over x minus -1. F of x is 2x squared minus 3. And let's just evaluate. -1 squared is 1. 1 times 2 is 2. 2 minus 3 is -1. So f of -1 is -1. That becomes x plus 1 at the bottom. And if I go ahead, excuse me, in the numerator, when I go ahead and simplify, I get 2x squared minus 2 over x plus 1. Now, when I go ahead and plug in a -1, I'm going to get 0 over 0. I have to do something with this. That numerator does factor. Can factor out of 2. And then I have difference of squares. And then the x plus 1s will cancel out. So if I go ahead and evaluate right now, actually I'll just go ahead and plug in. Let x equal -1. -1 minus 1 is -2. -2 times 2 is -4. So f prime of -1 is -4. The slope of the tangent line to the curve at x equals -1 is -4. And yeah, it kind of looks like it. Let's see how good I did. If we go up 1, 2, 3, 4 over 1, I came close to eyeballing it. So there you go. That's how you can find that. Now, we actually haven't answered the question yet. All we've done is found the slope. Remember what the question was find the equation of the tangent line, but we've done the hard stuff. Now we're going to write the equation of the line. And there's different forms, but the easiest one for these is your point slope form. If we do this, whoops, and plug in for what we know, the point on our curve, remember we just did this actually. When we plugged in a -1, we got -1. When we plugged in -1, we got -1. So that's our x1, and that's our y1. So y1 is -1. x1 happens to also be -1 in this problem. So y minus y1 equals m, which we just found was -4, x minus x1. And then we'll just clean this up a little bit. So y plus 1 equals -4, x plus 1. It is okay with me if you leave your final answers in point slope form. It's a useful form, so that's totally acceptable. However, if it is multiple choice, you may see the answer given in y equals mx plus b form. So just distribute your slope, subtract 1 from both sides, and here's the same equation or same line given in slope-intercept form. Either form is fine with me. But now we know the equation. And again, this seems to make sense. A y-intercept of -5, it does look like we're hitting down there around -5. So this seems like a reasonable answer. So there is your equation of tangent line. So the idea, if you're trying to find the equation of the tangent line, you can use this. You can also use the other version and then just plug in -1. The other version for the derivative, plug in -1 at the end. This is a much easier difference quotient to work with though. So most people, when you know the value you want to plug in, most people just go with this one. All right, here is, oh no, I have it all worked out. Hopefully you didn't see it. Try this one on your own, and I meant to erase that. So try this one at the very bottom of the screen. Try that on your own, and then pause the video, and then unpause it, and I'll reveal the answer. Okay, let's take a look. So I meant to erase that. I have it right here. So here it is, all worked out for us. Again, we're going to find the slope first. Now, another form of notation that you may or may not have seen, I showed you that dy dx for a derivative. If you want to show that you're plugging in 9 for x, then you put a vertical bar and you say at the bottom of it, x equals 9. So this means the derivative evaluated at x equals 9. And we know the formula equals the limit as x approaches a of f of x minus f of a over x minus a. And if we tried to plug in right now, we would get 0 over 0. This has square roots. That thinking conjugates are going to work with this. So I tried multiplying the top and the bottom by the conjugate. Here's the numerator. And then the denominator I just left in factored form. Oh, look at that. X minus 9s cancel out. And then if I take the 9 and plug it in for x, I do get a value. We have a continuous function, so we know this will work. I have the derivative evaluated at x equals 9 is 1/6. So the slope of the tangent line to y equals the square root of x at x equals 9 is 1/6. 1/6 is not a very steep slope, but that makes sense. If I do a very rough sketch, y equals the square root of x, that's the one that does something like this. By the time I'm over here at wherever 9 is, you can see the tangent line is just not that steep. So this value does seem reasonable. But we still don't have the equation of the line, so let's go ahead and find that. To find the point, I need to know what the y value is when x is 9. The y value will be 3. So my x1, y1 is going to be 9, 3. x1, y1, there's my slope. I can distribute the slope and then add 3 to both sides, and I will get this equation. Either form is fine. Woohoo! So that's pretty much it. I do want to just show you something really quickly, though. I'll show you a couple of things. So remember how I said you could use the other version of the limit instead of this one, but this one's easier to work with? So take a look at this, and I do have, here's the other version. If I tried to first do this, the x plus delta x version, it works. I get down to here, and then when I go ahead and evaluate at x equals 9, plug in a 9 here, I'm going to get that same value of 1/6. It works, but you can see that this is a lot uglier, a lot more work, but there's nothing wrong with it. So I encourage you to pause the video and just take a look at that and see how that worked. But compare this, all of this, to just this part, and it's much nicer. This part's much nicer. So there was that part that I wanted to show you. And then just really quickly, I'm going to go back to Desmos here. So here's example 4 again, that last example we were just looking at. And again, I apologize, when I'm at Desmos, I don't have any way of pointing on the screen. If anybody knows of an app that will let me like use my pencil as a laser pointer on the screen in general, I would love that. But you can see the blue curve, that's my square root function. The point right now, I just want to show you how I can move the point, and this is the tangent line to the curve. See how the that black line just kind of rocks and rolls all over the curve, but it just touches it at one point. If you take a look over on the left-hand side, you can see that at the very top of the screen, there's my f of x equals the square root of x. G of x represents the derivative, 1 over 2 root x. And then if you look 1, 2, 3, 4, 5 lines down, you can see that a, f of a. That's this red point that's moving along the curve. So and you can see at the bottom the actual value for a. A is 5.2. I can put it over here where a is 9. And there's my slope of 1/6. If you were to count the rise over run, you're going to get 1/6. But Right above that, y minus f of a, that's my y minus y1, equals g of a, remember g is my derivative, so that's my slope, times x minus a. That's why the derivative itself often has an x in it. Again, going back to the derivative g of x is 1 over 2 root x, because the value of the derivative will change as x changes. Right now, the slope of the black line, that's the derivative when x is about 2. Now the slope of the black line is the derivative when x is about 6. Now the slope of the derivative is when x is about 10. So the value of the derivative will change as the slope changes. And that's why we have an x in our answer. So hopefully that makes sense. And then the sub should give you, maybe they've already given it to you, the homework packet. And so you've got the homework you can get started on. And then I will see you guys when I get back. Bye.